The human body is approximately 60% water, making each of us a walking reservoir of billions upon billions of hydrogen atoms. Deep within the nucleus of those hydrogen atoms lies a subatomic property called quantum spin. Because a proton has an electrical charge, this spin turns every single hydrogen nucleus into a microscopic magnet, complete with its own north and south pole. In our natural environment, thermal energy constantly tosses these atoms around. Their tiny magnetic axes point in completely random directions, fiercely colliding and overlapping. Because these individual magnetic fields point every which way, they cancel each other out to a net zero state. Consequently, our bodies remain completely invisible to magnetic detectors in everyday life. That changes the moment a patient slides into the enclosed bore of an MRI scanner. They are immediately immersed in a massive static magnetic field, known to physicists as B0. The overwhelming power of the B0 field strips away the quantum chaos. It forces those randomly oriented hydrogen protons to fall into line, aligning their magnetic axes either parallel or anti-parallel to the machine's primary field. A slight majority of the protons will settle into the lower energy parallel state. While the difference is tiny, only a few protons per million, it is enough to create a cumulative macroscopic force called the net magnetization vector, which points straight along the longitudinal or z-axis. We now have a strong magnetic signal. But there is a problem. This net magnetization is perfectly static and locked in the exact same direction as the scanner's own massive field. The machine's receiver coils cannot detect it against the background of the B0 field. Creating order out of chaos is only step one. To actually extract data from the body, we have to violently knock this perfectly aligned system off balance. Even when aligned with the B0 field, these protons are not standing perfectly still. The torque from the magnetic field interacts with their angular momentum, causing them to wobble around the z-axis, much like a spinning toy top leaning in a gravitational field. This behavior is called precession. At the quantum level, the nuclear dipoles trace a conical path around the central magnetic axis. Looking at this illustration and the accompanying Larmor equation, we see the mathematical rule governing this motion. The speed of the precessional wobble is strictly dictated by the strength of the external magnetic field. A stronger field creates a faster wobble. At the magnetic field strengths used in clinical MRI machines, the precessional frequency of hydrogen falls squarely within the radio frequency, or RF, spectrum. Knowing that exact frequency gives the scanner a precise tuning dial. It allows the machine to target and communicate exclusively with hydrogen atoms, ignoring the rest of the body. To disrupt the system, the scanner fires a brief burst of energy called a radio frequency, or B1 pulse. This pulse is tuned to exactly match the hydrogen proton's Larmor frequency. Perfect resonance causes protons to absorb energy, tipping the net magnetization vector away from the longitudinal z-axis, down into the transverse xy plane. The RF pulse also forces individual protons to synchronize their precession, wobbling in phase with one another. The exact moment the RF pulse is turned off, the protons are left projecting a synchronized rotating magnetic field that rapidly sweeps through the transverse plane. According to Faraday's law of induction, a moving magnetic field will induce an electrical current in a nearby conductor. As the proton's magnetic vector sweeps past the scanner's receiver coils, it generates a tiny alternating current. That induced current is called the free induction decay, or FID. This is the raw echo, the actual signal the scanner records. The signal does not last. The moment the RF pulse stops, the protons immediately begin returning to their original low-energy equilibrium state along the z-axis. This diagram outlines the decay process. First, the protons experience T2, or transverse relaxation. They lose their synchronized rhythm and drift out of phase with each other, causing the transverse signal to rapidly cancel itself out and decay. Simultaneously, we see T1, or longitudinal relaxation. This is the slower process where the protons release their absorbed energy into the surrounding molecular lattice, allowing the net magnetization to gradually climb back up the z-axis. While T1 and T2 relaxation occur at the exact same time, they operate at completely different rates depending on the physical environment the hydrogen occupies. It is the specific rate at which this signal fades that gives physicists the data they need to distinguish one type of tissue from another. This graph highlights the clinical payoff. Hydrogen protons locked inside dense fat molecules relax and release their energy at a vastly different speed than protons floating freely in water or cerebrospinal fluid. Their relaxation curves diverge. The scanner's computers measure these microsecond timing differences and assign them specific shades of gray. Fast-recovering tissues might be mapped as bright white, while slow-recovering fluids fade to black. An MRI image is literally a map of quantum decay. By manipulating the microscopic spin of the hydrogen atom, engineering and physics translate subatomic behavior into one of the most powerful diagnostic tools in medicine.